So I started angular momentum, I am going to continue with that. If there are any further questions, you can ask me right now before I go into about harmonic oscillator or any other thing. Okay. So in the harmonic oscillator, interestingly, there was a degeneracy, two-dimensional harmonic oscillator, there is a degeneracy of the levels. The ground state is non-degenerate, the first excited state has 2 states, the second one will have 3 states, third one will have 4 states, etc., etc. Okay. Yes? Any question? Fine. So now I told you this angular momentum operator L is R cross P. And as you know, angular momentum is related to rotational transformations, okay, rotational transformations. Now, this will have 3 components, L, Z, Lx, Ly. Lz I will only Lz I will write, Lz will be Ypz minus Zpy x. These are all operators. I am not putting that caret on top of it. These are all operators. Okay. Now, as I mentioned earlier, you can diagonalize Lz, one of the generator, one of this angular momentum operators, and you can from there one of the generators, and the other 2 will not be diagonal, it is not be diagonal matrix, but L square, okay, will be diagonal, because it commutes with all of them, it commutes with all of them. So, this is basically the idea. Now, if I take L, so let me write x, y, z, okay, let me write x, y, z, the position operators, and then I can ask the question, what is Lz with x, with Lx? I can construct that. It is Ypz x, this is Py here. Have I written it correctly? No, sorry, this is not correct. This is xpy minus ypx, ypx, okay. That is what we will have, R cross P will have. Now, I ask the question, what is Lz with x? Okay, Lz with x will be, you can work out the commutator, right? You know how to work out these commutators, all of you. It is very simple. If you have commutator of, this is what you have to use, just for your benefit. If I want AB with C, commutator of matrix is AB with C, what you have to do is, this will be equal to A with B comma C plus A comma C with B. That is a matrix formula, nothing to do with physics or anything, simply matrix multiplication. Because AB, this is using the fact that AB, this thing itself is AB C minus CAB. This is what that equation is. So, if you expand this, you will find it to be this. You write this, then it will be ABC minus ACB. Similarly, ACB minus CAB, that is what the 2 terms which are there, you will find exactly what I have written on the left hand side. So, using that you can work out all these commutators, okay. You will expect, so this is what is there, and I will tell you what will happen. This is what is called rotations, because XYZ, Lz is a kind of an operator which leaves the z part invariant, does not touch it, but xy plane it rotates. So, this is x axis, this is y axis, and this is z axis perpendicular. This whole plane is rotated, okay, whereas L is the z part of it is untouched. That is what is axis of rotation is z. That is the meaning of that object, and we know what is going to happen. And I will tell you what is going to happen. When you rotate it, when you rotate this, it will go to x prime, y prime, z prime. And as I told you, it is an axis about z axis. So, z prime will not change. Z prime will not change. So, if I write this as a matrix multiplying x, y, z, since z will not change, this has to be 1. This is 0, this is 0, 0, 0. Z has not changed. So, it is only xy plane which is rotated. Okay. Now, you know what will happen there also, it is very simple. It is cos theta here, sin theta here, minus sin theta here, cos theta here. That is what that object is going to be. Okay. That is what that object is going to be. Now, I can, this is as simple as that. It is as simple as that. Now, I can write this matrix, okay, in this form. I will write it for you. I will write it as e to the power I theta and then a matrix which is Lz. I will call it Lz. Okay. Now, what is that matrix? So, if this thing is there, you can expand it. E power I, you can expand it. The first term will be 1. Okay, first term will be 1, and that first term is simply multiplying identity matrix multiplying x, y, z. What is the second term? What is the second term in that expansion of e power I theta z? You know e power x. You know e power x or not? What is it? 1 plus x square by factorial 2 plus x cube by factorial 3, etc. As simple as that. I am not. So, the first term is, this is 1 here plus I theta times Lz. I will put a dot dot dots. For small values of theta, I can keep only to the leading order. If theta is very small, if theta is 0, nothing happens. If theta is 0, x prime y, there is no rotation, you go back. If theta is very small, this is x axis, this is y axis, I rotate this whole thing by a small amount, 1 degree or half a degree or 1 minute or 1 second, whatever you want to have, very, very small amount. You do not have to worry about what you are writing for the higher terms. So, that is what I am put this rest of the terms as dot dot dots, okay, because I want to know what is Lz is. So, this is a transformation, Lz is a transformation which gives you for very small values of theta. Now, I should know what is the small values of theta. When theta is very close to 0, cos theta is 1. So, that matrix is 1. This is 1, let me write 1. And what about sin theta? It is theta, you should keep up to first order, right? You should keep up to 0. Sin theta is 0 is correct when theta is 0. But I am not saying theta is 0. Theta is equal to 0 is identity. I am not making any transformation. But I want to make small transformation, right? Infinitesimal transformation. So, I should keep theta but to the order theta. I should drop theta square and theta cube, etc. So what is it? It is equal to theta. This is theta, this is 0, and this is minus theta, this is 1, 0, 0, 0, 1. That is what the first term is going to be. The first term is going to be that, right? Now I should then, what if this is equal to this whole thing, if this whole thing, okay, that is what that matrix is. So what is LZ? What is LZ? You already have theta, so you can say, sorry, it is equal to this whole thing. You can subtract 1, you subtract 1 from this, then you will get I theta LZ. I theta LZ is this matrix minus 1, right, minus identity matrix. So I theta LZ is 0, 0, 0, because the 1 will cancel out. Then you will have I theta here, sorry, it will be theta minus theta, I am kind of thing, and then, so this is that matrix. So I can even write this theta outside and this theta outside and call it theta here, right. I can cancel this theta also on both sides. So ILZ is what is that matrix, okay, ILZ is that matrix. So what is it I can do? If I know LZ, if I know this LZ, which is LZ, which is, for that I should multiply by minus I. If I multiply by minus I, it is minus I, 0, 1, 1, minus 1, 0. Okay. You can even put that I inside. You can even put minus I here, and this minus I and minus 1 will become I here. So LZ is that matrix. LZ is that matrix which has done a small rotation, right? It has become a small rotation. Now if you know that matrix, I can substitute it here. Once you know this matrix, I can substitute it here, which means e to the power I theta LZ, where LZ is this matrix. You have found out what is LZ. So you simply write the exponential of that matrix. Whatever formula is there for e power x. E power x is, I said, 1 plus x squared by factorial 2, x cubed by factorial 3, etc. is true even for matrices. E power a, as a, where a is a matrix, is 1 plus a square by factorial 2, where a is a matrix, a cubed by factorial 3, etc. If you do that, you will exactly get this matrix. You will exactly get. So you should, first term is going to be this, which we have, that's what we have used. The second term from there will turn out to be square of this matrix, and the square of the matrix is exactly what you have for the other terms, right. When you keep up to the leading order, second order, up to second order, cos theta is, it starts with 1 plus theta square by 2. Sin theta is theta, the next term is theta cube, do not bother about it, right, only up to theta square. Similarly here, and this one will be 1 plus theta square by 2. So that is what you will get from this matrix. So to all orders you will get the same thing. So that is what is the first thing. So I told you what is LZ. Similarly, I can work out what is LX. I can work out what is LX, I can work out what is LY by considering the same kind of matrices which I wrote. I wrote if it is, say, I wrote cos theta, sin theta, 0, minus sin theta, cos theta, 0, 0, 0, 1. This is the LZ part which I wrote. The L, the matrix which I wrote, not LZ, the rotation up to angle theta along keeping Z axis as an axis of transformation. Now, if it is x axis, I keep rotation about x axis. So, what is that matrix? I want to keep x axis invariant. That means my axis is x, I rotate this room in this way, right? This is y axis, this is z. So, in this plane I rotate. So, what will be that matrix? So, the same cos theta, sin theta, minus sin theta will appear in different places. It will be in the yz plane, right? It will be in the yz plane, in which case this will become 1, this will become 0, this will become 0, this will become 1 sin theta, and this will become minus sin theta, and this will become cos theta. This is the rotation about x axis, similarly for y axis. So, each one you can work out Lx, Ly, Lz. So, now you have 3 matrices Lx, Ly, Lz. You already have 3 matrices Lx, Ly, Z coming from xpy minus ypx. So, you wrote down a commutation relation. You wrote down a commutation relation based on this one Lx with Ly is I h bar Lz. So, I am dropping that h bar for this is a commutation relation. I can write for Ly Lz and then Lx Lz also, all the 3 of them. There are 3 commutation relations I can write and they obey that. Now, I have given a matrix form for that, because what is that matrix which I wrote for you? It is this matrix. If I have this matrix 0 I minus I or minus I here plus I here, if I keep this as Lz, similarly I work out Lx, similarly I work out Ly and find that commutation relations of these matrices. Matrix multiplication is all of you are familiar. You can multiply 2 matrices AB minus BA. You will find exactly identical. Okay? So, that is why we call this Lx, Ly, Lz. If I want to do small transformation, use Lx times theta or Ly times theta or Lz times another theta, 3 angles. You can rotate by small angle about z axis, y axis and x axis. So, if you do that, that matrix will give you the answer for it. It is 1 plus that theta times I theta times Lz. That matrix will give you. If you want to find large rotation, big rotation, not theta is not small, 30 degrees, 25 degrees, 50 degrees. If you want to do such rotations, what you should do is find what is for small transformation and exponentiate it, e to the power I theta Lz. You build the full transformation using small transformations. You make the 30 degrees transformation by a small amount. Okay, that is what it is. It is like you build the high speed by small speeds, right, from 0 to something. That is what you are doing. So, that is why these objects like Lx, Ly, Lz or L, which I have written down, they are all generators. They are all called generators of rotation. They are all called generators of rotations. Okay? Is the meaning clear? Okay, that is what you know the small one, you can build the big one. You generate the big one by exponentiating the small ones. That is all you are doing, and that is what this thing is. And you have this object which obeys the commutation relations here, and I have given an explicit representation or explicit matrix form which is for all the three matrices. But you can ask the question, are these the only matrices which can be there? Because you know, if I work out for this matrix, if for this matrix say L is Z, for this matrix Lx, Ly, Lz, for this I can work out what are the eigenvalues of Lz. The eigenvalues of Lz will turn out to be 1, 0 and minus 1. Okay? And you can also find out what is Lx square plus Ly square plus Lz square. You take this as an exercise. You work out Lx, Ly, Lz, find out Lx square plus Ly square plus Lz square. Square of the matrices. All the squares will turn out to be identity matrix. You will find that Lx square plus Ly square plus Lz square is equal to what? Huh? Huh? Yes. Be bold, tell me. Huh? No. Well, there is a factor, small factor which is in front. You will find it to be equal to L into L plus 1, where L is 1 now. 1, 0 minus 1 I said. So, it will turn out to be 1 into 1 plus 1 which is 2. The answer is 2. Okay? You will find it to be 2. So, what you are having is, which I am going to show, the values for L square are going to be L into L plus 1. The allowed values for L square are L into L plus 1, where L square is Lx square plus Ly square plus Lz square, and the values for Lz, which are also diagonalized. You can diagonalize any matrix. You diagonalize for the general convention because it matches with spherical polar coordinates Lz. You will find it to be minus L to plus L, minus L plus 1 and then minus L plus 2 till you reach plus L, right? Minus L plus 1 till L plus 2, you go up to some value which is plus value, plus L, that is all. So, there are 2L plus 1 values for that. So, this is what is the thing is. So, I have given you explicitly one representation of L is equal to 1, because we know these are all rotations in 3 dimensions. Okay? The matrix, the representation which I have given you in the parlance of group theory, it is called the fundamental representation, what people call as a fundamental representation, or in this case it turns out to be what is called adjoint representation. These are all only words, you can forget it. So, this is what is a structure. Given this, I am going to look at the angular momentum theory briefly. So, what is it you have to do is, I have, let me call Li Lj or sorry Lx Ly is I Lz, Ly Lz is I Lx, cyclically Lz Lx is I Ly. These 3 objects, that is what your R cross P is, and this is the thing. What are the sizes of the matrices which you can find for Lx, Ly, Lz? Already I have found one. I have found already one, okay, which is the 3 by 3 matrix. 3 by 3 matrix is explicitly I found for you, right? It is only rotations. So, can I find something more? Can I find for L is equal to 2, L is equal to 3, L is equal to 4. So, L is equal to 2, what will be the size of the matrix? What will be the size of the matrix? L is equal to 2. 5 by 5 matrix. You all agree or you disagree with him? He seems to be a nice guy. He says it is 5 by 5 matrix. Do you agree or disagree? Or you don't have any opinion? What is your vote? Yes or no? Huh? Please tell me. I don't want to lose all of you. He says L is equal to 2, means it's a 5 by 5 matrix, right? So many heads are doing this, which I agree, they are all agreeing, and rest are keeping quiet. It is 2L plus 1 dimension. 2L plus 1 is 5 dimension, and he is right. Okay, 5 by 5 matrix. So you should find Lx, which is 5 by 5 matrix. You should find Ly, which is 5 by 5 matrix, and Lz, which is 5 by 5 matrix. Okay, these are the ways in which you should find the matrices. Now, if L is equal to say 3, what is the size of the matrix? 7 by 7 matrix, which means you should find a 7 by 7 matrix of Lx, you should find a 7 by 7 matrix of Ly, and 7 by 7 matrix of Lz. Correct? That is what you should get. Perfectly right. Now, this is the way in which people find what are called explicitly. In group theory, they call it representations. Representation for L is equal to 1, representation for L is equal to 2, etc. Okay? Now, I will give you, I have already given you this matrix. Whatever I wrote here, Lz, I wrote here I minus I 0. This is the matrix I wrote. Similarly, you can write for Lx and Ly. Okay, you can write, and that will satisfy all the 3 equations. Okay, all the 3 equations it will satisfy. You agree with that? Now I write a new matrix. I will call this as Lz1. Okay. Now I am going to ask Lz2. That matrix is Lz1 0 0 Lz1. I have written here. Similarly, Lx2 Ly2, and this is simply Ly1 0 0 Ly1, and similarly for Lx and Ly, right? This is x here, x here, and similarly for this. I have given what is called 2. What is the dimension of that matrix? What is the dimension of that 2, Lx2 or Lz2? Huh? What is the dimension? What is it I have done? I have put only the same matrix here and here, that is it. I have taken Lz. Anyone has an answer? How is it 5? This is 3 by 3 matrix. This is 3 by 3 matrix. This is 3 by 3 matrix. No, 6. It's only 6, which has one block on the first and the second block in the second thing. So it is like this. This block is, this is one block, and this is one block. Everything is L here, the same L. So it's a 6 by 6 matrix, right? Is that agreed? Will it, this new L2, will it satisfy those equations? Right? It should satisfy. It is simple. I have not done anything, right? I have not done anything. I have only put 2 of the same thing. Okay, I have put 2 into 2 4 and 3 into 3 9, and then put 2 as a matrix. There is nothing. So you have not generated anything new, okay. You are having the same representation which you have written in many blocks, Now this kind of object in group theory is called reducible representation. It is called reducible representation. Okay, you can block diagonalize it. You can make it into two blocks, each one of them, and each one of them satisfy that equation. So that is not giving you anything new. It's only what you know already is you are putting it in different blocks. So this is reducible. So what I want now, I can ask the question, can I make this Lx, Ly, Lz which I have given, block diagonalize it? Can you do it? Well, you cannot do that because Lx will involve these two and Lz involves these two and Ly will involve these two, okay, first and third, okay. So they mix all the three. There is no way you can write it as block form, all of them in the same block form. So that representation is called irreducible. You cannot reduce it further. I am trying to teach group theory without actually using the words group theory, okay. I am trying to give you the same thing which is there in group theory by using words which are there, which is only matrix representation. So this is basically the idea. Okay. Yes. It is only LZ2 is only LZ1 in two blocks. Okay, it's the same thing appearing in one block here, another block here. It's block diagonalized. Okay, every block satisfies the equation, so the whole thing satisfies the equation. That's all I am saying, right? Okay. So what we want is set of all irreducible representations. Okay. Now there are ways of constructing it, but I will try to do some physics ways. I told you Lz is an angular momentum, magnetic quantum number along z axis, and the values are 1, 0 and -1. Okay. It corresponds to angular momentum L is equal to 1. L is equal to 1, magnetic quantum number is 1, 0, -1. Okay. Now I take, so there is a magnet or there is a spin with spin 1, and then it can point along z axis with +1 or -1 or 0. These are the three values allowed. Now I take two such objects. What are the angular momentum of the composite of two objects? What are the angular momentum? So first one is also, second one +1 will go to 2. Okay. Similarly, -1 along with -1 will go to -2. 1 and then the 2 and -2 are easy. Now then I do this object. The first one is 1, the second one is 0, right? Second one is 0. What is the total value? It is 1, right? 1 plus 0 is 1. So you can have 2 and then 1. I can have both of them to be 0, then 0, then I can have -1 and 0, which is -1, and -2, but -1 and -1, which will give you -2. Okay, this is what I have done here. I will try to draw the diagrams. 1, 0, -1. I have 1, 0, -1, two such objects. I can go to 2 by having both of them 1. This and this I can go to 1. This and this also will give to 1. And then I can go to 0 by 0 here, 0 plus 0, or I can go to 1 minus 1 which is also 0, and minus 1 0 which is also 0, and then I can have minus 1 with 0 will give you minus 1, and minus 1 0 and minus 1 will give you minus 1, and then minus 1 with minus 1 is minus 2, right. This is what I will get. If I have two composite of two spin 1 particles, spin 1 objects, if I have composite of two spin 1 objects, what will you get? You will get all these states. Now, what are these states? What are these states? It starts from 2, 1, 0, minus 1, minus 2. That is what you called as angular momentum L is equal to 2. It will have 5 states. Angular momentum 2 is 2, 1, 0, minus 1, minus 2. So, this is, I will call L is equal to 2. I will call this as L is equal to 1. I will call this is L is equal to 1. This is L is equal to 2. Okay. Now, what are these things? What are these things? L is equal to 1. So, and what is this? L is equal to 0. So, when you have a composite of two spin 1 objects, you will have a spin 2 object, you will have a spin 1 object, you will have a spin 0 object. Okay, this is what is the thing. Now, when I say spin 2, spin 1, etc., I should be able to write down, when I write down a matrix for this combination, okay, I should be able to get a spin 2 object in it, spin 1 object in it, a spin 0 object in it. Okay. So, now what is the dimension of the composite object? The composite object consists of both. There are 3 states here, there are 3 states here. The composite will have, everyone hesitates to say, even if it is wrong, tell me. 9 states will be there, right? Because it can be any combination. I goes from 1, 2, 3, 1, 0, 1, 2, 3, 3 states. J goes from 1, 2, 3. Ij will go from all possible ways, 3 into 3, which is 9 states. So, this composite object will be a 9 by 9 matrix, Out of this, this is the 5 by 5 matrix, this is a 3 by 3 matrix, and this is the 1 by 1 matrix. So, you are able to write that as 9 by 9 matrix in the form of 5 by 5 matrix, 3 by 3 matrix, and 1 by 1 matrix. Now, you know only already L is equal to 1, I construct the matrix. By this process, I can get L is equal to 2, because that 5 by 5 matrix I can easily work it out. How do I work out? That is another one which is there in what is in matrix theory. In matrix theory, you have a matrix A, let us say it is M by M matrix, and another matrix B, which is another M by M matrix. You get a matrix C. What is the matrix of C? It is again 3 by 3, right? You take the row and column, that is what you do, and that is what you are getting. Now, there is another product which you can take, okay? This is what is called matrix product. Another product which is called direct product, and it is written as A cross B. Okay, I will tell you the rules for that. I don't know whether you are aware of it. I will tell you the rules for it. Here. I will tell you the rules for it. What you have to do is the following. I will tell the rules with some simple example. A is a 2 by 2 matrix. We will have A11, A12, A21, A22, right? A 2 by 2 matrix. Incidentally, in AB cross C, AB is equal to C, the number of number of columns in A should be equal to number of rows. That is what needed. N cross M, you can even a rectangular matrix, N cross M, you can multiply by M cross P, but that M should be equal. How? If there are something like so many rows, the column should be exactly equal, otherwise you cannot multiply. That is the rule, but generally we multiply square matrices of the same size, there is no problem. But here I am going to multiply A cross B, where B is a 3 by 3 matrix. A is a 2 by 2 matrix, B is a 3 by 3 matrix. Now I will tell you the rule for A cross B. I will tell you the rule for A cross B. First of all, in this case, A cross B will turn out to be 6 by 6, the 2 into 3, 6 by 6 matrix. I could have started with both are 2 by 2 matrices, in which case it is a 4 by 4 matrix. You will have a 4 by 4 matrix, but just wanted to make life a little more difficult for you by having a different size matrix. Okay? So what is it you have to do? A cross B is A11, so this is that thing, A11 multiplied by B, A12 multiplied by B, A21 multiplied by B, A22 multiplied by B. Remember, B is a 3 by 3 matrix, right? For your benefit, I am going to write only A11B for this alone. Okay? This alone I am going to write. You can write the same way this all the three. It is A11, B11, this one, A11, B12, A11, B13, A11, B21, A11, B22, A11, B23, and then A11, B31, A11, B32, A11, B3. That is that first term, first block. Okay? That is a rule for what is called the direct product of two matrices. Direct product of two matrices. That is what you have as a rule. So, what you are doing, as I told you, how many, what is the dimension? It is 2 into 3, which is 6. If I had multiplied a 3 by 3 matrix with a 3 by 3 matrix, direct product. If I had multiplied, what will be the size of the matrix? 9 by 9. So, that is what I did in the previous example. This example which I have done here, I have taken this matrix, I have taken this matrix, I have taken the direct product of those two matrices, which is what I have constructed the 9 by 9 matrix. But that 9 by 9 matrix, okay, I have constructed in such a way that it is a spin 2 block, spin 1 block, spin 0 block. Say 5, 3, 1, right? That is the way I have constructed. That is what is the, okay, forget all these things. So now I am going to give representations of all other things, a simple way in which it can be obtained. Some of these things are there in regular textbooks, so I am going to be minimal about it. Is there any question? Any question? Okay. I think I am doing very well. That's why nobody has questions. Okay. I will start with LZ and L square and LZ are diagonal for B. Both are diagonal matrices. So, which means to specify this I will have L, I will specify this with M and I will call that as M, L, comma M. Okay. What is the meaning of this notation is it is a column vector. Different eigenvalues of M, Lz, okay, in that basis, diagonal basis, I write this thing. This is the standard notation in quantum physics. What they use the ket notation. Ket to tell me it is a ket vector. It is a vector which is a column, various values of M which is there. So, like 1, 0, minus 1. For example, let me write for your benefit L with plus 1 is actually this state. This is the vector. L with minus 1 is 0, 1, 0, that vector, and L is equal to, sorry, M is equal to, M is equal to, M is equal to 0, and then M is equal to minus 1 is 0, 0, 1. Okay. This is the meaning of this object and this object and this object. So, I will write this notation. You did earlier harmonic oscillator where you have the ladder operators A dagger and A. Similarly, I will have ladder operators which is 1 by root 2 Lx plus ILy and 1 by root 2 Lx minus Ly. These two are ladder operators. Why are they ladder operators? They take any state with value m, it goes one step above m plus 1 or m minus 1, okay, m plus 1 or m minus 1. Yes, any question? So, it is a ladder operator. It is almost like, for example, in Hermite polynomial, you are multiplying a polynomial with x power n, it goes to x power n plus 1. You differentiate with respect to d by dx, it goes to x power n minus 1. So, one power is increased, okay, one state is increased, that is what is the thing. Same thing is happening for A daggers, etc. Here also the same thing is happening using the fact that you can work out, take it as an exercise, what is Lz with L plus minus. Take it as an exercise, Lz with L plus, you can work out with Lx, L plus is Lx plus ILy. So, what I am asking you to work out is Lz with Lx plus ILy. What is on the right hand side? I have already given the commutation relation, you are already having that, okay. And Lx, Lz, Lx minus ILy, both of them. You find out for both of them, you will find very interestingly, I will give you the probably the answer, it will turn out to be plus or minus L plus minus. L plus will take one step above, L minus will take one step down. It is a ladder, right? L plus will take one above one thing. It is very simple to work out. Now, what is the, I think there should be probably a factor of I also, you can work out. You check, this is probably a factor of I. Okay. Now, the interesting result is, if you have a state with M, if you have this state with M, Lz with Lm is M times Lm. Now, you can ask L plus acting on Lm will give me a new M prime. It will give me a new state, because it is not an eigenstate of Lz, right? It is not an eigenstate of Lz. This, sorry, it will be, sorry, it will give me a new state M to M prime. It is not an eigenstate of this, there is no eigenvalue equation here. It will turn out this is an eigenstate of Lz. It will be an eigenstate of Lz using this relation. Using this relation, you will find Lz acting on L plus Lm is equal to M plus 1 times L plus Lm. That is, this whole thing is a new state, M prime, and this thing is an eigenstate of Lz. L plus acting on M gives me a new state, that state is also an eigenstate. Same thing happened for harmonic oscillator. You had N, the state N, A dagger acting on that gives you a new N prime, but it is an eigenstate of A dagger A. Okay, number operator. So that is what happens here. So what you start with M, some value, by L plus you can go up one step. You can go one step. Now you operate again on this, you will go one more step, like this. You will keep on going by L plus acting on that somewhere, right? Now, unlike the case of harmonic oscillator, for this case it should stop at some point. It cannot go on, and that is very simple result coming from the fact that Lz cannot go beyond L. The eigenvalues of Lz cannot go beyond L, okay, the value L which you started with, where L is connected to the L square. L is connected to the L thing. How do I know it? How do I know it is from this thing. For me, Lx is a Hermitian operator. Lx is a Hermitian operator, which means it will have only real eigenvalues. When I say real, it can be positive and negative. It can be positive and negative. Okay, positive and negative. Now, if I take Lx square eigenvalues are, if you have A has eigenvalues A1, A2, A3, square of that will have A1 square, A2 square plus A3 square. That is all. The square of eigenvalues, square of a matrix has eigenvalues whose square of the matrix itself, the really thing, as simple as that. Because you can diagonalize it, and then when you diagonalize it, you will have only square of that. So this is what you are going to have. This object Lx square will have only, will it have negative eigenvalues? It will not have any negative eigenvalues. That kind of matrix is called positive definite matrix. If all eigenvalues are positive, it is positive definite eigenvalues. Similarly, Ly square is also positive thing. It will have only positive eigenvalues. Now, L square we know is Lx square plus Ly square plus Lz square. L square is also positive. Okay. Now I take this Lz here, L square minus Lz square is equal to Lx square plus Ly square. Correct? It's simple relation, which says L square minus Lz square should be positive, which means Lz square cannot exceed L square, right? It cannot exceed L square, otherwise it will become negative, right? It will become negative. So Lz is bounded, Lz eigenvalues square is bounded by L square. It cannot go above that. But I was just giving you that I start acting on M, I go to M plus 1, M plus 2, etc. Beyond some value, it has to stop. Otherwise, it will not obey that. So that place where it stops, I will call it as L plus L, and M is equal to, it stops at M is equal to L, is 0. That state annihilates that. It is a state which is annihilated by that Lz matrix, L plus matrix, L plus matrix. So you start with M is equal to some value, like say 4 or say 1, you may go up to 2 and then 3 and then that's it. L plus acting on that has to be 0. Similarly, L minus acting on Lm will give you new M double prime, and L plus Lz acting on L minus L min will be equal to M minus 1 L minus Lm. So what is L minus is doing it? Instead of going up, going down. Okay, it's like there is a 30-story building, you are in the 10th story. If you take the lift, you can go to the up, you can go up or down. That's what is happening here. That's why it's called ladder operators. Okay, again, by the same arguments, it cannot be lower than some value. So at some value, it has to be annihilated by the same argument. It turns out very easy to prove that the value will go from minus L to plus L. Minus L to plus L. The M value will go from minus L to plus L. You start somewhere in between any value, acting by L plus again and again, you will go to the highest value. Acting again and again by L minus, you will go to the lowest value. And the number of values is from minus L to plus L, which is, if they are integers, you know the number of values will be 2L plus 1. You take any number 5, you start from minus 5 to plus 5, how many integers are there? Okay, that is all, 2L plus 1, as simple as that. Now with all these things, I am going to, I am speeding up, I am trying to give only the gist of the thing, little more details I can work it out, but that is what is done in any class in quantum mechanics, quantum theory. Probably those of you who have not taken quantum classes will find it the same thing repeated with little more calculations done. Those who have taken up quantum mechanics classes, you might have seen it already. So I will give you the answer, because I want to go to at least something new beyond what is going to be taught or what is already taught in quantum mechanics classes. Okay. So Lz is going to be a diagonal matrix. So it is going to be Lz the state is labeled by this object m times Lm, L square acting on Lm is given by the value is not is L into L plus 1 times L comma m. Now I should tell what is L plus acting on Lm and what is L minus acting on Lm. That will give me all the matrices. All the matrices which you know, these are all diagonal matrices. This is identity matrix. This is identity matrix with eigenvalue L into L plus 1 diagonally. All of them are same. This is not identity matrix but diagonal matrix. It is a diagonal matrix. For example, we had 1 0 minus 1, L square will be 2 into 1 1 1, this is L square, this is Lz, and I should tell you what is L plus, L minus as a matrix, 3 by 3 matrix. Okay. I have already given you what is Lx and Ly in that case. You can simply add Lx plus Ily, that will give you L plus and L minus, right? That is nothing new. But anyhow, I will give you the answer for arbitrary L. I will give you for arbitrary L, any L. For any L, the answer is the following. L into L square root of L into L plus 1 minus M into M plus 1. So, plus or minus here, that is it. And then the state is not an eigenstate, so I should get M plus or minus 1 here. Acting on the state Lm, L plus will give you L M plus 1, L minus acting on that will give you M minus 1. There is a coefficient which will come because the state should be normalized, okay, it should be normalized. So, if you want to, if you start with Lm is normalized, that is a norm of the vector is 1, that is M comma M prime, the two states, integral is equal to 1, then this is additional normalization you will get. Okay. So, this is the result actually. So, I realize my M plus 1 has gone outside, so be careful. So, it looks like whatever I write here will not be seen there, is it? Whatever I write here is not seen there, or they change the camera, I do not know. So, I will you have to let me know because I realize only now. Okay. So, I will write it at least. That is it. Okay. So, that is your angular momentum. That is your angular momentum, and we have already worked out 3 by 3 matrix. 5 by 5 matrix is easy to write down. Now, you put L is equal to 2 and M is going from minus 2, minus 1, 0, 1, 2, you will get 5 by 5 matrix. You can do for any number which you want, you can put even million. If you are capable of doing million by million matrix, you can do that. But what we need is 0, 1, 2, 3, not even 3, 0, 1, 2 is enough. Okay? That is the kind of thing which you have as what I called as representations of angular momentum algebra. There is a name for it. Whatever is written is called generators of the angular momentum, which is called Lx, Ly, Lz. They obey an algebra. Then the technical words are they obey an algebra, which is what I wrote to you earlier. Lx, Ly commutator is I, Lz, and the 3 commutation relations, and the representations of that algebra will be given by such matrices. Okay, it is called, that is as simple as that. Okay, if you, what this generator will do for you is, once I have this, once I have Lx, Ly, Lz, I can take e to the power I theta times L, that matrix, which means theta 1 time theta x, let me write explicitly, if you take theta x Lx, theta x Lx plus theta y Ly, theta z Lz, okay, that will do the transformation for arbitrary rotations. For arbitrary rotations, what does the Lx, Ly, Lz tell you is, for small rotations, infinitesimal rotations, what is the change? This is the difference between, if you know what is infinitesimal, you can easily exponentiate to get the full glory arbitrary transformation. Is that clear? Yes or no? So that is what is done everywhere. Now, the value of L is, the value of L is 0, 1, 2, all integers. In mathematical notation, that is that Z people write. Okay, the integers, that's what you, any value you have the matrix, any value you like. Okay, that's what is the way in which you have. Okay, that's why in hydrogen atom the same thing is coming. For L, for that L value is restricted by principal quantum number n. It cannot go beyond n. So n should be less than L. L should be less than n. But n can go up to infinity. It can go over 1, 2, 3 up to large number, which means L can also go up to large numbers for the corresponding value. Higher and higher orbits will have higher and higher angular momentum. This is what you have here. Now, I can do one thing now. I have to introduce something new, and that something new is what you learn from hydrogen atom or electron. What you learn from electron. The electron has orbital angular momentum in hydrogen atom. If you remember, it is NLM. N is the principal quantum number, L is angular momentum, M is magnetic quantum number. That is what you are taught, right? All of you are taught this 3 things, and the N is going to be, 1, 2, 3 up to infinity. L is 0, 1, 2 up to L, up to N, N minus 1. M is minus L to plus L, minus L to plus L. This is what you have. Okay, but electron as funnily has a spin value. That is what we realized. The electron, even at free stage, when the free electron is there, it can be spin up or spin down. How do we know that it has spin up and spin down? I don't know whether you have heard of this famous experiment called Stark effect. You have a bunch of electrons coming, and then there is a magnetic field which is applied. The spin up electrons go up and spin down electrons go down, and you will make a point on the cathode ray oscilloscope on one side and here. That is what happens, which means the bunch of electrons can exist in 2 different states, and the 2 different states we call it as spin up and spin down. 2 states. If the thing is corresponding to angular momentum, what is the spin value of that? two stage, I said 2L plus 1, right, 2L plus 1 equal to 2. If 2L plus 1 is equal to 2, 2L must be equal to 1 and L must be half. We call it spin angular momentum, spin value which is half, spin half, spin half. Spin half will have spin up and spin down, or half plus half, which is called 1 0, 2 by 2 matrix, minus half is 0 1. This is spin up and this is spin down. Okay? This is what is there. I suppose I am going outside slowly. Be careful. So you have to tell me when I am going outside. So this is what you have for, yes? So this is what you have here. I think I probably should stop with here, somewhere here. I will put it. Okay. Because he has fixed the camera and gone. Okay. So if there is a spin half representation, I should be able to give the L plus, L minus and Lz for that. Okay? L plus L for that. Okay? So I am going to give that. So I can work out, let me call it as SZ, because it is spin. Instead of LZ, I will call it as SZ. It will have spin up and spin down values, and that matrix which is diagonal, and I will call it as half 1 minus 1, right, half and minus half eigenvalues. There is a name for this matrix. There is a name, this is called half sigma Z. People call it as Pauli spin matrix sigma Z. Similarly, I can have S plus, S minus. I have given you the formula. What is L plus acting on this thing, right? From there you can work out what is S plus minus. That will turn out to be half, is going to be half sigma x plus I sigma y and plus or minus. Now what is sigma x and sigma y? Sigma x is going to be 0 1 1 0 and sigma y, if I am right, it is going to be I minus I. There might be a minus I also is possible. Okay? So that is what the three matrices, sigma x, sigma y, sigma z, which are called Pauli's sigma matrices. Pauli's sigma matrices. The angular momentum, spin angular momentum is half times sigma. Half is the number associated, plus half and minus half. So this is what is the thing here. So if you look into that definition which I have given you for angular momentum, it works very well even with half. So it allows value for the half value. It allows for the half value. It allows for half value also. Okay. Now, what is the difference between integer and half integer? Why is it you don't have in hydrogen atom? Hydrogen atom has only orbital angular momentum. When it rotates around, like Earth rotating around the Sun, it has only integer values. But the spin part of it, which you can imagine it to be rotating about itself, there is no truth in it, but rotating about itself, it has a plus half and minus half, and that is given by this. Okay? Is that clear? This is a fundamental difference. The fundamental difference is the following. So you start with some spin up state 1 0, okay, 1 0 state. If you are rotating about z axis, just z axis, the generator for that is sigma z. So you will calculate I sigma z by 2, because that generator is I by 2. Generator is sigma z by 2. Sigma z is not the generator, half of that is generator. You should remember that factor of half. If you have that, sigma is it, when 1 plus I sigma will give you small rotations. If you do small rotations, if you do large rotations, this is what you have to compute. This is what you have to compute. If you do large rotations, you should exponentiate. If you were exponentiating for orbital angular momentum, you should do it here also. If you do that, it will turn out to be, take it as an exercise, expand it, and the interesting thing is all the sigma x square is equal to sigma y square plus sigma z square is 1 identity matrix. You can easily work it out. You can even find out the algebra of sigma matrices, which is using the factor of half. Remember half. So that is the way you should work it out. If you do that, I have taken only a simple example here. You can do arbitrary angle also. This will turn out to be equal to, the matrix is cos theta by 2 plus I sin theta by 2, cos theta by 2 minus I sin theta by 2, 0 0 multiplying 1 0. Yes. So this is what you have here for this object 1 0 etc. So far so good. Now I rotate my z axis, about z axis by an angle 2 pi. That means this is my z axis, I rotate this whole room about this axis by 2 pi. So you have come back to the same point. You have come back when you do 2 pi rotation. Now when I do 2 pi rotation here, this one cos pi by 2, this is sin pi by 2, 0 etc. You will find it does not come back to its original value, because theta by 2 is there. It is not theta. Cos theta 2 pi is same as cos 0 is same as cos 2 pi, but cos pi is not, cos pi is fine, but sin pi. So cos pi by 2 for example, because pi by 2 if you do that, or cos pi and sin pi if you do, there will be differences, the sign differences will be there. So what has come is, if I do 2 pi rotation I do not come back to the same value. If I do 4 pi rotation, then you come back. The state, okay, the state has become, when you do that rotation 1 0 or spin up, go to minus this thing and then come back. Okay, that is what happens in the case of spin half particle. 2 pi rotation does not bring it back to the original value, whereas it will do for integer angular momentum. There is no problem for integer. Whenever it is half integer, then 2 pi rotation will not bring it to itself. So these representations are called, the name for that is spinorial representation, whereas the other ones are called vector representation, vector, tensor, etc. Whereas spinor representation, under rotation 2 pi, you do not get the same state but negative of that state. Okay, if you start with 1 0, you will have minus 1 0. That is what you will have. Okay. So this is the beauty of spinorial representation as compared to vector representation. Now that is where my final punchline is going to be. After that I will tell something more. The spinor, like electron, has spin half particle. Okay. You might be taught, I don't know, in statistical mechanics classes somewhere, this kind of electron behaves like fermions, which means if I take a wave function for two particles, psi 1, psi 2, the wave function for two particles we will write it as psi f 1 comma 2, or let me write 1 comma 2, or phi 1 r1 r2 for two particles, okay, and the two particles are identical particles. You cannot distinguish them. It is a very important concept, identical and indistinguishable particles. If you have an electron here and another electron here, you put this electron here and this electron there, that state is identical to the previous one. You cannot distinguish it. Okay? You cannot, two electrons are identical and indistinguishable. Now, if I exchange two particles, you expect it to be psi of r2 comma r1. Okay, the wave function will be psi of r2, which is equal to the old value. This is what you expect. This is what you expect. It turns out there is a minus sign. It turns out there is a minus sign. And without that minus sign, your atom cannot be stable. That minus sign is coming from the fact Pauli's exclusion principle, which says that you cannot put two electrons in the same state. If you have two electrons in the same state, the probability for that should be 0, which means in the hydrogen atom, in the ground state where n is equal to 1, you can have one electron. If you want to put the other electron, you have to put, if it is spin up, this should be spin down. Now, if you want to put the third electron there, you cannot do that. In the ground state, you cannot do. You have to go one step above. N is equal to 1, 2. You have to go. Then, how many electrons can be there in n is equal to 2? You can have n is equal to 2 means L is equal to 0, comma 1. Right? L can be 0, comma 1. In L is equal to 0, comma 1, again the 0 can be spin up and spin down, and 1 can be 1, 0, minus 1 and spin up and spin down. So, total number of electrons in the first, other than the ground state, one excited state, is going to be 8 electrons. So, the first orbit ground state will have 2 electrons, then it is full. The room is full, you can't put anything more there. When you go to the next thing, you are going to put 8 electrons. After that, it is full. You have to go above. When it is full like 8 electrons, when it is full like 8 electrons, it does not want to interact because it does not want to admit any other fellow. Okay? So, they are the inert gases. In chemistry, you will find they are all the inert gases which come about. So, the Pauli's exclusion principle helps in understanding the chemistry table, Mendel's table of what are the stable elements and what are the things which interact. Sodium will interact with chlorine or sodium chloride, etc., because you cannot put, if this is one electron down and that is one electron can accommodate, they will join together. There is a room here and there is a person, extra person there. So, they can join together. So, like that it happens. So, this leads to this profound principle which was used to explain the stability of atoms, which is called Pauli's exclusion principle, and fermions obey Pauli's exclusion principle. Pauli's exclusion principle. Fermions obey Pauli's exclusion. Now, this famous theorem, and the theorem is spin statistics theorem. Any integer spin particle obey bosonic thing, that is plus 1. Any half integral particle obey the fermionic particle. There are only two kinds of particles, one is bosons, another is anions, fermions. These are the two things, and that fundamental nature of this thing comes from the theory of angular momentum with half integral values and integral values, which is allowed in the case of this thing. Now I have this last question, 2 minutes is there in my watch. Is that okay? Okay. So I told you in the case of two-dimensional oscillators, two-dimensional oscillators, you have the states are, the ground state is n is equal to 0, n comma m, 0 0, degeneracy, there is no degeneracy, one state is there. The next one is 1 0 comma 0 1, there are two states. The next one is 2 0, 1 1 and then 0 2, there are three states and so on. Okay, it goes in the same form as that. It seems to match with angular momentum theory, right? So there is some angular momentum which is coming there, but unfortunately that angular momentum is mysterious, because that angular momentum which you expect, if at all there is a two-dimensional harmonic oscillator, you can do rotation about xy plane. You do not have z plane to rotate, you have only two, right? How does a three-dimensional angular momentum come in this thing? Okay, that is the question. Some of you should think about it, and but I can give you one clue, and the clue is there are two oscillators, which is p square plus x square, px square plus py square plus y square, half of it. This is your Hamiltonian, which I can have an creation operator here, A dagger A and A dagger. For this I can have B dagger B, this is my Hamiltonian. So you have two creation operators and two annihilation operators, A dagger A dagger B, B dagger. What is the commutation relation? A dagger is equal to 1, B dagger is equal to 1. Now I will give you, you can work it out, this is another exercise. You construct A dagger B, A B dagger, and then A dagger A minus B dagger B. I will call this as Lx, and this, L plus, L minus and Lz. I will call this way, okay. Construct the commutation relations between these three objects, A dagger B, A B dagger and this, and probably a factor of half. Okay. You construct that, unfortunately it will turn out to be exactly your angular momentum algebra. Okay, and that is an exercise you can report to me by tomorrow morning or today evening. I am going to stop here.